All right, let's start chugging through some slides. Like I just mentioned a few minutes ago, next week is finals. So like we're almost out of time. We have 3 classes left to cover 6 chapters. No, it's not 6 chapters. We'll get through most of it. I think we'll be all right. All right, so right now we're talking about inter-process communication. So this is the ability for multiple processes to talk to each other through various means. And some of the reasons we might want them to talk to each other is sometimes one process is waiting on another process to finish its stuff. So a process might have to sit there and wait or do something else while it's waiting for the part that it's relying on another process to do to finish. So those processes need to have some way of sending messages. So a couple ways we do that is through shared memory and message passing. So shared memory would be a global memory location that both processes have access to, maybe through a pointer. Pointer would be kind of the old school way of doing this. The newer, there's actually system calls for shared memory where a parent process can grab a chunk of shared memory, and then any of its child processes, when they grab it, they'll get the same chunk of shared memory. So that would be considered the more efficient way of doing it, I guess, rather than having to pass pointers around. And then message passing would be directly sending stuff between two processes. One of the common ways of doing that, kind of maybe the global idea of message passing would be that you actually send a real message to another process. Sometimes you don't actually need to send a message. You might just need to send a signal where, two processes, because the programmer is the one who wrote those two processes, wrote the code for it, they know that there's only one thing that they're waiting to hear about. So they don't need to wait for a specific message. They just wait for them to be signaled that it's okay to go, kind of like passing the baton. Okay? But even within that, there are multiple signals that can be raised, like with unique IDs. So signal 1, signal 2, signal 3. So you could have multiple messages that really don't have meaning beyond, I'm waiting for signal 3, that type of thing. So those would all fall under the category of message passing. Just something else to throw in right here. This kind of supports what Evan was saying about me sticking on one slide. Oh, was that you were joking to me about that, right? Fail. Um, but something that often gets thrown into inter-process communication when you kind of look at it is something called a semaphore, which is actually for resource sharing. I'm assuming that'll be somewhere in here probably. But a semaphore is a way to have things queue up for like a printer, something like that. Some resource where only one dude can be using that resource at a time, and the semaphore is a way of controlling that in a way that doesn't allow for race conditions, doesn't allow two processes to grab the same resource at the same time. So just kind of trivia information that sometimes those things get thrown into inter-process communication where it's not really communication between processes, it's more of a referee type deal. All right, stupid. We just said that. This is the whole concept of why we need inter-process communication. Some processes run solo, some need to cooperate with other processes. Stupid. Oh, this is just an example of shared memory. Actually, this is the dumb version of shared memory where they're passing around pointers. Another trivia piece of knowledge, if you're ever looking at code on Google or something like that, often whenever you're just creating an array to store some stuff, shared memory stuff, it's usually called a buffer. And really where that came from is the way you used to read in strings is you would use a function called scanf. or scanf was the newer version that actually specifically read in strings. And what you would do is you would pass it the pointer to the array, the character array that you actually want to fill up, and it would fill it for you. And that the kind of the common naming convention for that array became buffer. So something, if you see that, it's chances are it's for reading something in. Bounded buffer, that sounds like something from one of Evan's storybooks. Oh, the consumer bounded buffer, that's from Evan's storybook. What was this one? Oh, the producer, that's Tim. You skipped breakfast. Yeah.
Who's in a parade?
Parade or Solly's? Seriously.
Solly's, but I got paid for the parade.
How much did you get paid?
Paid for the parade because it was for work.
Was it, whose turn was it to buy anyways?
Mine.
Yeah, that really wouldn't have worked out in your favor.
Spend money or
Make money, yeah, that's... Oh, did you see yesterday Solly's had 2-for-1 Butterburgers during the Packers game? Epic. How many of you in here still have not had a Butterburger from Solly's? That's just terrible. There needs to be a finals week field trip. I don't think you know it. This is the crap they're serving in heaven. I'm not lying. There's a contract. Yeah, we actually had a conversation about this at a dinner Bible study. My pastor was there, and my pastor said he thought the burgers had too much butter. So then I called the owner of Solly's and put him on speakerphone. True story. All right, message passing. I kind of already explained it. You get it. Stupid. 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 Stupid.
what is life just not worth it anymore now that you found out that everyone is in Solly's?
Well, most people, all the important people in here at Solly's, except for Angela. She has an excuse. I went to Solly's the other day with her husband, and who's British, very British, by the way. Oh my gosh, he's British. Yeah, we had dinner. We had Thanksgiving dinner at their place, actually, and they cooked for 40, and there was 5 of us. There was more sides than there were people. And they knew how many people were coming. It's not like it was like a poor turnout. It's ridiculous. It's ridiculous. Well, anyways, he was going to bring her back a Butterburger, and I forbade it. I forbade it. No, because then the butter has to be all melty and dripping and all over your fingers and kind of down your face and lubricating the insides. You know, if you take it to go, it becomes all gelatinous. When butter, like melted butter, dries, you know what I'm saying? You're not getting the same product. I wasn't going to let that stand. So you actually have to go there. All right. Well, synchronization, just a general comment about this. Their crap down here is stupid. But this concept of synchronization kind of comes down to that idea where I said multiple processes might be running at the same time and reliant on each other. So they have to sync up in some way. A lot of times that's done through signals. As far as signals are kind of the easy way of message passing. You know, throw up a flag, and anybody who's interested in this signal can grab it. So this is just the mechanism by which, or the idea that processes need to, sync their watches, if you will. Buffering, I already told you about this. This deals with the reading crap in. Shared memory would probably use this idea of buffering. It's going to be an array somewhere up in memory that you can fill with crap, and different processes can read from it. Let's see. So here's an example from POSIX. This is kind of a Unix standard. POSIX compliant. It's kind of like IEEE, but for programming on Unix. So shared memory uses this SMGET, shared memory get. So this is what it takes in, and it gets a segment ID that you can then pass around. Waiting access to shared memory must attach to it. So shared memory is this thing up in the sky, and if you need access to it and you need to read from it, you have to attach to it. So think of it like a telephone that you're calling. When you're done, detach from the shared memory, because the more things that the more individual processes that are attached to it, the more the memory manager has to do, to keep everything kosher. So just an example. Just another standard mock, which is mock the Mac? I'm confused. I think mock is Mac. Like old, not now, but old. Oh, Windows XP, whatever, stupid. Oh, here, this will show us the actual. Look, it doesn't even give us code. Local procedure call. Message passing centric just makes it sound smart. Just dumb. Completely stupid. All right, still stuff with Windows. Okay, so communication in client-server systems. So this is different than processes specifically talking to each other. Well, it's still processes talking to each other, but not child processes of the same parent. So this would be like two separate programs that need to communicate with each other in some way. So that's why they're saying client-server. So for instance, we use client-server models all the time. If you've used a web browser and you go to Google, Google.com is the server. They're the web server up there, and your client is the web browser you're using. And those two programs work together and accomplish crap. Okay? So within this client-server type model, we have various tools for communication. One of them, probably the most common, is this idea of a socket. So a socket is like dialing somebody's phone number and leaving the connection open. That's a socket. Okay, so you connect to a remote IP address. So when your web browser is hitting Google, we're connecting to Google.com's IP address, their unique address, on a specific port. Web browsers or web servers are usually port 80. So your web browser, if you didn't know this, if we type in Google.com with Concordia's bad internet, doesn't go there. All right, Google.com, it takes us there. Same thing if I say Google.com port 80, so :80, it'll take us to the same place. Trust me, it will. If it doesn't work, it's totally an internet thing. This works. But in any case, so the web browser automatically tacks on a port 80 unless you specifically tell it a different port. I'll just let that cook. We'll come back to it. The internet was doing funny things this morning anyways. So anyways, socket connection is your standard connection between two programs. We call it a client-server type situation, but it doesn't have to be that. When I say client-server, that just typically means one person is connecting to, the other one is serving information. You could have situations where both programs are both sending and receiving information, so they're kind of both acting as clients and servers. So client-server, just descriptive terms. All right, so sockets are our most common communication channel. Remote procedure calls, these are substantially more recent and really never took off. RPCs, as far as I know, were really born out of Java. There was probably some predecessors to it that weren't called RPC, remote procedure calls. But the idea of this is there's a network layer that sits above your program. So if we talk about it in terms of Java, a network layer that sits above your Java program, and it links programs that are in two separate locations. All right, so client server, if you will. And rather than opening up a physical socket connection to this guy and sending data over that socket connection and having the server interpret it, that very much becomes kind of a, you're going to have to format it in like JSON or some way, some formatted string for that communication. Like you tell it, I need this kind of information, and then it parses it and determines what you asked for, then sends it back. So instead of having to do that, you can actually call remote methods, passing them the exact parameters that you might want. So you take out that middleman of having to create strings and parse strings, because it's being done for you through a standard, the RPC standard. So now you can just remotely invoke a method that lives on the server, passing it the exact parameters you need to send it, and that method knows what you're asking for because you called that method. Realistically never took off, which is kind of funny, because doesn't that sound on paper better? It sounds more specific, doesn't it? The problem is I think there's some performance issues with it to begin with, but on top of that, now you have to write a zillion different methods to do something, which makes sense for local programs. But when you have remote programs, it's sometimes harder to create documentation for that, as opposed to an API that you always connect to the same port, and you just pass it different JSON queries or something like that based on what you're interested in. So in any case, remote procedure calls never really took off, but they do exist. A pipe is usually communication between two programs on the same machine. So kind of like a socket, but it's like a local type thing. So you would pipe information into another program. Remote method invocation. So this is the Java thing. This is off of remote procedure calls. It was the evolution of that. Okay, so keep in mind this is not inter-process communication. This is inter-program communication, I guess is a reasonable way of putting it. So these are just additional tools for communicating between two programs. Having said that, is it possible for two processes that are both child processes of the same parent to open up a socket connection to each other? Technically, yes. You'd be hacking it. What you would have is you'd have the parent who splits into two children. Parent forks two children, Abe. Okay? Each of those children would then set themselves up as a server. So they would create a listening socket on a particular port, but a different port. So maybe the first child is listening on port 2000, and the other child is listening on port 2001. Child number 2 can now connect to child number 1 on port 2000. Child number 1 can connect to child number 2 on port 2001. So you could sort of kind of use sockets for inter-process communication if you have the two processes set themselves up as servers, socket servers. So having said that, sockets do not have to be remote. A socket connection is to a IP address and a port. So you can connect to the local machine through something called localhost, which is like the synonym for this IP address. The IP address version of that is 127.0.0.1 is localhost. Or you could actually use the physical IP address of the machine, which then is going to require it to head out and then come back in because it doesn't know it's local. So it'll be less performance. You don't need an internet connection to even be alive to hit localhost or 127.0.0.1. So you could pull off inter-process communication using only sockets. It's possible, but it would be a hack. Okay, I already talked about this. See, what do we even need these slides for? That's why we stay on one slide for so long, Evan, is because I know all of it already. I just spit it out, then we skip all these slides. What's up? Setting. What was I talking about? I know all this, but I don't know where I am. That's been happening to me lately. I've been getting confused. kind of concerning. I might have something going on. I found myself completely lost in my own bedroom the other day. Isn't that weird?
You haven't been eating as much, so your body's wondering what's going on.
Something. I put some cereal away in the microwave.
So now it's borderline, just like you might not be able to live.
Yeah, I'm like an invalid. Right. And I've always kind of like, even though I'm crazy, I've always kind of like very much relied on like my sharpness. And now if I'm getting lost in my own house, it's the beginning of the end. I guess the good news is I have a pretty good sense of humor. So if I'm going to get dementia, I think I'd probably roll with the punches pretty well. What was I talking about? Oh, sockets. We already talked about this. Socket communication, also already talked about this. Here's the multiple ports, web server, port 80, blah, blah, blah. So, got that. Remote procedure calls. We have something called stubs. That's like a, when you preface the, this actually is a modern day, well, more modern day version of an old school programming technique. In the C programming language, you used to have prototypes for your methods because it was a one-pass compiler. If you were going to call methods down here, you had to prototype them up here. And why is that? Well, if you needed to call a method, let's say you had two methods down below, method A, method B, and you defined method A first, then method B second, you couldn't call method B from method A because it hadn't been defined yet. Does that make sense? Because it was a one-pass compiler. So to get around that, you used to prototype your methods up top, where you would just write little stubs. Not the actual method implementation, but you'd let the compiler know all of these methods will exist and this is how you call them. Not what they do, but how you call them. Make sense? So that later on, when you wrote a piece of code inside of method A to call method B, it would know what the compiler could say, yes, this is legal because you prototyped it up above. I know you've called the method correctly. Does that make sense? So stubs are really born out of that because in a remote procedure call environment where you have two programs that live in physically different places, in order to call methods down here, you have to create the stubs up above, the prototypes, to let them know what you're going to, that these are legal. Kind of have to register with that network layer that lives above. Those are called stubs. Not really that important, just more of a trivia piece of knowledge stuff. I'm sure it'll be heavily represented on the final. In fact, I would almost guarantee it will not ask anything about stubs. It's stupid. So, actually, I'm deciding, is it stupid? So I am a very big advocate of knowing all the different like names of stuff so you can have intelligent conversations at Best Buy. I don't think stubs would ever come up, though. I would say it's acceptable to not know the word stubs and what it means. But you have to know sockets. You know sockets. You probably should know POSIX, too, just from a historical perspective. You don't really need to know what it is, just it's some sort of Unixy standard thingy. That's probably good enough, but if somebody says POSIX to you and you like glaze over, you're not going to get the job. Okay, execution of RPC, dumb, already talked about it. So pipes acts as a conduit allowing two processes of communication. So this is kind of like the local thing. Talked about it. See, this is the question, can pipes be used over a network? So, sockets are the upgrade to pipes. So we used pipes before sockets, before the internet really existed, or before networking really existed. Sockets ended up being pipes over distances. And there's not really a great reason why you can't set up local sockets either. So at some point in there, pipes probably became obsolete. They stay supported because we do have a bunch of really old programs that were written in terms of pipes that only communicate within a single system. And if the operating system doesn't support the pipe system call, those programs would all break. Okay, but chances are you're not writing stuff with pipes today. Ordinary pipes. That required a picture? Named pipes. Whatever. Questions on chapter 3? Chugging along. There's so much fluff in there. Wrong button. We're not using that. Look at that. You can't even use Microsoft Office without clicking on 50 things. We're still on Megan's MacBook. It's got to be an old connection. Let's see what we're on today. Nathan's iPhone. That's Apple's crappy Bonjour protocol for you. Yeah, you see, it's something with, I'm guessing, it's something with their Bonjour protocol. Apple's like easy to use named networking stuff. But I think every single device, every single Apple device broadcasts a Bonjour name. And there must be like a default where if you don't connect specifically to something, it just grabs something. Probably either the first or the last element in there. Hopefully it's not a random one where they actually did it on purpose. Like, we just got to connect them to something. Because I think the Bonjour network isn't a broadcast network. I think it's a linked network. So every device has to connect to every other device to kind of keep it in line, if you will. So I'm hooked to somebody's iPhone. Oh, threads. We should be able to turbo through this. Because we already talked about a lot of thread stuff, right? All right. Know what threads are. Know about multiple threads. Talked about multi-core crap. This is somewhat interesting. So a multi-threaded server architecture, this would be the idea of like our modern day authentication systems. So think about, we'll just use the example like an Amazon. So when you connect to Amazon, you're going to put in your username and password and press enter, right? Or click the button. Whether you actually do that or not, it's getting done. I know when I launch my phone and the Amazon app, my stuff's already in there, but it's still authenticating behind the scenes, right? How many people do you think connect to Amazon at the same time? A lot. A lot of people. Okay, what if you had to wait in line? Right. So this is where threads really thrive in this type of situation. So think of the Amazon authentication server as somebody who's taking phone calls. So it's a single phone that you're dialing by IP address. Okay. So the authentication server is going to hear the phone ring. So that's Tim trying to log in. Pick up the phone, spawn off a thread, hand that communication socket, because a socket is created there. Hand the socket off to the thread to authenticate Tim, hang the phone back up, waiting for Evan to connect. Phone rings, pick up, spawn it off, hang it up. Amish connects, so on and so forth. And that's happening really, really quickly. Make sense? Okay. Without threads, we wouldn't be able to pull that off. Without threads or being able to fork processes, we wouldn't be able to pull that off, Abe. I assume, Abe, you'd prefer a forked process as opposed to a lightweight thread. Like a little meat. Hey. Hey, was that phrasing? Hey. Funny thing is, I tried to back out of it because I almost said meat on the bone. And that made it worse.
You just said it now. Is it really...
I know. I was just kind of saying that it was like almost double phrasing. Actually, would that counted as double phrasing or just extra bad phrasing? I'm not sure it even matters at this point. I'm so gone. I'm gonna have to go to church tonight and request an extra service. So in any case, that's how multi-threaded server architecture might work, where we have, see, we're spawning off a thread, resuming listening, blah, blah, blah. So in any case,
You're going to hell already and you're putting cereal in the microwave. I don't think there's much more you can do.
yeah, it's already, we're at endgame at this point. Yep. But where am I? Won't that be really funny in class if someday I really do get very confused in class? And I'm up here, and because it's like I'm always joking around, you just assume I'm kidding. And I just start freaking out. Where am I? Charlie! Did I tell you guys about that? 4th grade? I had a 4th grade teacher, Mr. Thompson. He was in the military when he was younger. He was an older guy. And in the middle of class, he had a war flashback. So he's in the middle of class. Dude just dives behind his desk. He's like peeking out the side. So this is a bunch of, it wasn't 3rd grade, 4th grade. There's a bunch of 4th graders sitting out in the audience as their teacher's peeking out, peeking around the desk. It's like, Charlie, stay down. It was awesome. I think a passing teacher finally went and got the principal, and the teacher was removed. We didn't see him again. That was awesome. It's the best part of elementary school. Oh, no. Actually, 6th grade. Mrs. Jackson, my teacher. I don't remember what we were even doing, but she had one of those, the metal music stand things. She was trying to pull it up, cracked it up, knocked herself out. Just collapsed to the floor. We just sat there. 20 minutes. She finally starts rousing, coming to. That was awesome too. I can't decide which of those. Probably the Charlie one was better. Really, the tiebreaker is when he was peeking around the desk. Hey. Okay. This is just talking about single core systems, how everything just has to happen one after another, after another, after another. We can't have things happening at the same time. Multi-core systems. Now we have the ability to actually accomplish 2 things at the exact same time with 2 cores, 2 core systems. Okay, so now that actually creates a more difficult problem for the process scheduler. Because now we have to make sure that the 2 things that are working on the separate CPUs won't conflict with each other, that they're not reliant on each other. Does that make sense? So this kind of goes into this idea that 2 processors is not necessarily better than 1 processor. It won't be twice as fast. It really depends on the types of programs, the types of things you're doing on the machine, what you're feeding it. So some things can't be divided into multiple parts. Changing a light bulb, for example, can't be divided into multiple parts. So as we get more complex systems, more cores on the CPUs, things like that, the CPU scheduler becomes more difficult. And this is going to be one of our limitations on new hardware. On nude hardware. It's going to be one of our limitations. That is, certainly we do have some heat problems. That's why we're not coming out with processors that have, really our top tier processor today that's really sold in any sort of bulk is quad cores, right? We got the hyper threading on them, so there's kind of 8 core ish type thing going on there through something called pipelining. I know AMD has they have a 6 core. They have an 8 core. Okay, I'm not familiar with it. It's possible their 8-core is similar to a quad-core with hyperthreading. I don't know. Doesn't matter in this example. But I know Intel has internal test processors that they're working with that have far more cores than that. I think that the rumor is they have like 128 core CPU, something like that, which I'm sure they probably have to have the thing dipped in near freezing liquid ether or something like that, because I'm sure it gives off a lot of heat. But one of the limiting factors for us is going to be, under normal conditions on our computer, how many things can we physically have happening at the same time? You're going to have diminishing returns over time, right? If we give you 60 cores, a processor with 60 cores, the chances of that outperforming something with 20 cores is probably fairly slim. So chances are we're not doing 60 things at once that we care about on our computer, right? So more cores isn't necessarily better. It has to be practical. So kind of something that plays into the whole multi-core world. User threads versus system threads. This just has to do with their permissions on the system. Unimportant. Multi-threading models, many-to-one, one-to-one, many-to-many. They just covered the bases. So this is many threads to one process, one thread per one process, which is your generic program. You launch one program, it's going to have in modern day operating systems, it's going to spawn exactly one thread. That is the thread of execution. When you spawn off multiple threads, those become child threads of the parent thread. All right. This is just stupid examples. Solaris, green threads. Nobody uses Solaris anymore. Dumb. This looks like a picture of something else to me. He got it. He's what? Everybody else is just starting to laugh now. Wait, I don't know if I get it now. Well. Stupid, 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 stupid. These are just dumb, useless. Thread libraries, these are the standard within the operating system for generating threads. We're used to dealing with them in Java. So Java is a virtual machine that sits above the operating system. So if you are dealing with the Java virtual machine on Windows, it's going to speak the language of the thread system for Windows. If you're dealing with a Java virtual machine for Mac, it's going to speak the thread system for Mac, so on and so forth. So kind of not all programs are necessarily created equal. You could have a Java program that you write once and it might outperform, maybe the Mac version outperforms the Windows version, which doesn't outperform the Linux version or something like that, just because of the thread implementation. So each of those virtual machines was ported to those different systems, and they're going to have the strengths and weaknesses of the underlying system. So every operating system is going to have their own thread library. Some of them are going to be stronger in certain aspects. Some of them are going to be stronger in other aspects. So there's kind of a trade-off type thing. So think of this as an API for threads within an operating system. Pthreads is one of them. So it's a POSIX standard for thread creation. So Unix operating systems is where it's common. So pthread example doesn't matter. Win32 API example, so this is their thread model, also doesn't matter. Java threads are managed by the virtual machine, typically implemented using thread model provided. See, I should have just written these slides. Again, Evan, this is why we don't need these extra slides. Just put me on a blank screen and just go until I get confused and dive behind the desk.
However, then when you start talking about something else and you forget where you are, You don't have something to get you back.
More true than it should be. More true than it should be. Seriously, it's terrible. But the nice thing with Java, because most of you have seen, we did threads in here with Java, right? So we've all seen Java multi-threading. Multi-threading in Java is far easier than if you were writing at system level stuff, writing multiple threads in C or C++. Those used to be something you would avoid in those languages unless you really needed it. Where now, creating multiple threads in Java is really simplistic. So if you even think something might benefit from multiple threads, just create one. It's not a hard thing. So that idea of Java abstracting it away and creating the idea of threads in a modern software approach, and then handling the details of the system level threads for you, has some benefit. But keep in mind, right off the bat, if you're doing threads for performance, you're doing threads for performance in an underperforming programming language. Because Java's interpreted, so it's not going to go as fast as other languages. Oh, fork, Abe. Yes. So semantics of fork and exec. This is execute system calls. Thread cancellation of a target thread, so that's telling a thread to stop working. Here's the signal handling stuff. So threads can signal each other to let one thread know it has already finished its job. Kind of an interesting example that I've historically done that we don't have time for in here, but I'll just talk about it real quick, is a multi-threaded merge sort. I think everybody in here has seen merge sort at some point, even the 250 people. Merge sort, we can just keep dividing up an array, right? Well, we could spawn off a thread for each part of those arrays. Make sense? And tell that thread to sort that portion of the array. And then each of those threads need to let their parent thread know that I'm done sorting mine, so now you can start your job. So the parent thread can start its merge, but it can't start merging its group of 4 buckets until it knows that its 2 child threads have dealt with the 2 buckets. Does that make sense? So that's where signals might come in. So it's a kind of an easy way of showing off the idea of signals with threads. Merge sort's a good example. Realistically speaking, let me just ask a follow-up question. With merge sort, does multi-threading merge sort actually improve the performance? It's a real question.
Is the parent doing anything else while it's waiting?
I guess doesn't matter. Let's say no. Parent's waiting to do the merge on the full list. I'm not sure that really matters in answering the question.
I would think it does, because
You think it does improve performance?
Yeah.
Okay.
Because you have the 2 children doing something at the sorting their own sections at the same time. So that's taking care of 2 things at once, I guess.
Okay. Anybody want to tell him why he's wrong? is that a hand, Dave? Go ahead.
Because if you make a thread, you have to split the time of the CPU.
You're sharing, your threads. So really, if you were doing it with multiple processes, probably, especially on multiple cores. Multiple processes on multiple cores, certainly true. But threads are all sharing the parent's same CPU time. So really, you're just making the job more complex. You're actually probably slowing it down by having the memory manager, having the parent who's doing their own memory management switch between threads. But kind of an interesting, from a signal handling perspective, it's an interesting model to look at because merge sort, maybe contrary to popular belief, is actually a fairly simple sorting algorithm. We don't like the 2 recursive calls, so Programmers tend to avoid it like the plague until they get comfortable with recursion. But for all of you who are taking 470 eventually, when does that offer? Is that next fall? Programming language theory class? If you survive the class, you'll love recursion at the end. It's a big if. That's probably our hardest class. You got to take it. It's really fun. That class is impossible. Like, you're really selling it here. It's the hardest class. It's impossible. You got to take it. It's fun. No, it is a really cool class. Thread pools. This has to do with management stuff. Whatever. Dumb. Semantics of fork. We'll just stop there for a second for Abe. Does fork duplicate only the calling thread or all threads? That's actually a good question. So what if, and so we only have a minute left, so we'll stop on this slide, but what if you have a process that's already spawned off multiple threads, and then you fork that process? Are you getting a copy of just the central thread, or are you getting a copy of all the other threads that were forked off? And at this point, I'm asking you to kind of speculate. Go ahead.
I think all of them.
Okay.
You're forking the entire process. You're forking the process.
What's the role of a thread for a process? So kind of approach this from the idea that you're the designer of the, and I know we're out of time here, so you can start packing up, but if you approach this from the idea of the designer of the language, chances are that original process spawned off those threads to do some work that probably doesn't need to be done again. Make sense? So when you fork the process, it would probably be, at the very least, less likely that the child process is going to need all those worker threads to do jobs that were already accounted for. So more than likely, it's going to split off just the parent thread, give you a brand new, fresh child thread as a result of forking, but without any of the child threads duplicated as well. It's more than likely what would happen. I would be very surprised if you found an operating system that didn't do it that way. Less about that you couldn't do it, more about the usefulness of it. Okay, so we'll stop there. We'll come back on Wednesday. You might have a quiz on Wednesday dealing with some of the stuff we talked about today. So maybe review this stuff. Otherwise, I'll see you then.